Hi everybody, and this is Craig Robertson with UNM IEEE, and today we're going to go over D flip-flops, T flip-flops, JK flip-flops, and SR flip-flops. Now flip-flops are just clocked latches. That's all they really are. It's some combinatorial logic with a clock attached. And all it really does is it updates and remembers your information going to the pulse of the clock. And this is probably the first clocked exercise you're really starting in 238, and it's really not that hard once you look at the characteristic tables and the excitation tables, and I'm here to kind of walk you through them. So let's go ahead and start with the easiest ones. The easiest ones are D flip-flops. So D flip-flop, that's a shorthand for it. And let's go ahead and cross that off so we don't get confused there. So a D flip-flop looks like this. This is the clock down here. This is the data input. And that's the data output. We always call the output Q, we call the input D for a D flip-flop. So what we actually look for in a D flip-flop is that'll be our clock pulse right there. And then D is the data going in. Q is going to be our output. So just remember that everything in this flows from left to right. So the characteristic table for a D flip-flop is actually, it's pretty simple. So it's D and then Q plus, right? So if D is 0 or 1, then Q plus will be 0 or 1. I mean, it really is just that easy. The key to a D flip-flop is if you send it a 0, it's going to remember a 0 until you send it something else. If you send it a 1, it's going to remember a 1 until you send it something else. And it'll overwrite whatever is a Q. So if Q is a 1 and you send it a 0, then it'll overwrite that 1. It'll write it to a 0, and it'll remember that 0 until the next clock pulse. And you have a 1 on D. So remember that a D flip-flop, it's kind of dumb. All it does is it remembers exactly what you sent it last. So that's the easy one. It's so the excitation table for a D flip-flop is really, it's just this. It's so the excitation table, this would be the characteristic table, which means given the inputs, what does the output look like? Now, the excitation table engineers can't spell very well apparently. So, the excitation table, that's given the outputs, what is the input? So, this one's pretty easy. All we do is we go, alright, well this is, if we know that Q plus is equal to 0 and 1, then we know the D had to have been 0 and 1, right? So the D flip-flops are pretty easy. It's really not that bad, and they're the most common ones. So you're lucky on this one. It's the easiest one is the most common, and don't get used to that because it never happens in engineering. So let's go ahead and go with the T flip-flop. Now the T flip-flop's a little bit harder, but not really. It's not too hard, and I think it only takes just a little bit to actually get it. So a T flip-flop, we have a T on the input, right? And then our basic clock, and then our Q for the output. Remember, the signals always go from left to right through that T flip-flop. So what the T flip-flop does in the characteristic table, and this is just a little, it's going to be a little abstract, but you guys are smart enough, you'll get this. So, if T is 1, or if T is 0 or 1, then Q plus will be Q, or not Q. So what does this mean? Let's take a closer look at this. So, it's this being the Q. So, if we have our T flip-flop with an input of 0, so a 0 is coming into the T flip-flop, and say our Q is remembering a 0, or our flip-flop there is remembering a 0. If we put a 0 into the T flip-flop, clock hits the upward strike, and that's when it changes, is on that upward strike there for the clock. Then what it's going to do is it's going to read that T flip-flop as a 0 or a 1. If it's a 0, absolutely no change happens. So it just keeps on remembering Q. If it's a 1, it changes, it toggles. That's how I remember a T flip-flop, is it toggles. It changes it over from a 0 to a 1, or from a 1 to a 0. So that's all it does, is it knots the output. So if I have a 0 here and I get a 1 in on the T, then it will change it from a 0 to a 1, or change it from a 1 to a 0. Now if I have a 0 coming in, absolutely no change happens, it doesn't even matter. But with the T flip-flop, just remember that the 1 means it changes the output from a 1 to a 0, or a 0 to a 1. It doesn't really matter. It doesn't really decide whether it likes a 0 or a 1 more. It just changes it if you get a 1 on the input. So that's how we come up with a T flip-flop. Now the excitation table here, so meaning starting with the output and looking at the input. So the excitation table for a T flip-flop is, so if your output is the same as it was before, then your T must have been a 0. And if your output is not what it was before, your T must be a 1. So this one is still pretty simple, right? It's I mean, it may take a little bit of thinking, but just think of the T flip-flop as the toggle flip-flop. So let's go ahead and move on to our next one, the JK. So a JK flip-flop looks like this, and it's a little bit different from all the others. So J and K, and then Q being our output, right? And so, and this is still our clock, so clock pulse. It still hits on the upward pulse of the clock. So a JK flip-flop, it's kind of like a latch, and I'll show you, kind of the truth table for what it is. So since there's 2 inputs, it has kind of a larger table. So let's do the J column, the K column, and then let's do the Q plus column. And the JK, it's really, a lot of people don't like them because you have to do a J and a K for it, but I find that it adds a lot of don't cares in my simplification in the end, which kind of makes my product of sums or my sum of products a lot easier to do, because you can group don't cares wherever you want. So keep that in mind too, is that JKs can be easier to use even though they require more circuitry. It's a little bit easier to hand punch the logic. So let's go ahead and set up our truth table. And I'll go ahead and give you the characteristic table out of it. So just like with a JK latch, what we're going to do is we're going to get a 0 and a 0. That will return Q. So it stays the same. We haven't done anything. We're giving it a 0 in and a 0 in. It will just remember. It won't do anything to our data. If we give, let's see, if we give J a 0 in, and we give K a 1 in, then it has the same effect of resetting it. It's going to give it a 0 out no matter what. No matter what Q was, whether Q was a 0 or if Q was a 1, it will return a 0 out for the Q plus, for the next state of Q, if we put a 0 on J and a 1 on K. Now if we do it the other way around, if we put a 1 on J and a 0 on K, then we're always going to get a 1 out, no matter what. No matter whether it was remembering a 1 or a 0, it will always get a 1 out of that function. Now, it's the big twist here is that with a JK flip-flop, when you have a 1 and a 1 on both input, then our output here will be Q naught. And you see how it's kind of useful is if you put 2 zeros on it, remembers Q. If you do 0, 1, it gives you a 0. If you do 1, 0, it gives you a 1. And if you do 1, 1, it gives you the opposite of whatever you were remembering. So in a lot of cases, it can be very useful. It's a little confusing to derive the truth table, but it can be useful in some cases. They're not as often used, but they are used. So it's always helpful to use them because there's really no substitute for a JK flip-flop when you need one. So let's go ahead and look at the excitation table, and we'll do 2 columns here. So if we know that Q and Q plus, if it's set up like that, then given that, we know that our inputs had to be J and K. And so let's go ahead and set this up like a normal truth table. Go 0, 0, 1, 1, 0, 1, 0, 1. So if we're looking at our present state, next state table, and we see that the present state was a 0, and the next state is a 0, well then we know a couple things. We know that J here, if we know that it stayed the same, then J was a 0, right? But we also know that it's returning a 0, so we know that J was a 0 and K could be 1 or 0, right? So as long as J is a 0, we don't care what K is. Do you see how that kind of works? So J's a 0 here as long as we're returning what it was before. Then we can also see that K can be a 0 or a 1. So that's kind of our excitation table for a JK flip-flop. And you can see how the K would actually simplify a little bit easier when you're doing your K-maps at the end to see what the inputs to the flip-flops are. Because there's a lot of don't cares, and we love don't cares doing K-maps. So let's go ahead and do the next one. It's the next one, if we get a 0 and then a 1, then we know it could be a set, or it could be a Q naught, right? So if we know that you're knotting it, so the knot of Q being Q plus 0 to 1, right? So this one could work. Or we could just be setting it, so it could be going to this. You see how K still doesn't matter? It could be a 0 or a 1. But in both cases, J is always a 1. So we can say 1 and don't care for K. So you see how this is kind of working out for us here. It's getting a little bit more simple. So let's look at the case if it's a 1, 0. So let's look at this case right here. So a 1, 0.